Hello everyone. This is lecture 5 of the subject analog circuits, and in this lecture I am going to discuss different types of current mirrors and multi-stage amplifiers, basics of multi-stage amplifier. So contents are in different types of current mirror. I am going to cover two current mirrors in this class. The first one is current mirror with base current compensation, and the second one is the Widler current source. After that, we'll discuss about the basics of multi-stage amplifier. So before starting this current mirror with base current compensation, let's firstly quickly review the basics of current mirror circuit. The basics of current mirror circuit. So as the name suggests, current mirror is a circuit in which the output current is the mirror of the input current. Okay? It means that I out will be equal to I in. That is a current mirror circuit. Now the next question arises that what are the properties and what are the applications of current mirror? Where we use current mirror? Why we are studying current mirror? So there are two main applications of current mirror, and the first application is it is used in biasing circuits. It can be used to bias the amplifier. Like you have studied the different biasing techniques in amplifiers, BJT amplifiers, MOSFET amplifiers. There is one biasing technique called biasing using constant current source. In that biasing technique, we connect a current source I. This is the negative supply minus VI at the emitter of the BJT, in similar way at the source of the MOSFET. This current source is basically the current mirror. In short, we are mentioning just current mirror with CM. CM is the current mirror. This current source is basically the current mirror. So the first application of current mirror is it can be used in biasing. And the second one is it can be used as an active load in amplifier. There is an advantage of active load over passive load, like gain is higher. Right? So these two are the main applications of current mirror circuit. And as far as properties are concerned for current mirror, as far as input and output resistance are concerned for current mirror, you can understand it. What will be the input and output resistance for ideal current mirror? Since in current mirror, the input is current, output is current. So, in order to avoid the signal loss, the input resistance of ideal current mirror should be 0 and the output resistance of an ideal current mirror will be infinite. You can understand with the help of same logic which you have studied during feedback amplifiers like voltage amplifier, current amplifier. Like in current amplifier also there is a input and output both are current. In current mirror also input and output both are current. So for ideal current mirror, the input resistance is 0. It should be 0 and output resistance should be high. And for ideal current mirror, R out should be infinite. So when we design any current mirror circuit, so we need to consider two factors. The first one is the output resistance should be as high as possible, and there should be minimum error between input and output current. The output current should properly track the input current. Now, there are different types of current mirror like basic current mirror, then after that base current compensation current mirror, Wilson current mirror, cascade current mirror. So here in this class, I will be focusing only on two current mirrors. One is base current compensation current mirror and other one is Widler current source. So if we go for basic current mirror, let's quickly review this basic current mirror. In basic current mirror, using BJT, we are taking two transistors. Let's say Q1 and Q2 are name of these transistors, and at the collector of Q1 there is a resistance R connected. This is supply voltage VCC. Let's say through resistance R, current is I reference and the output current is I out. Now to ensure that the collector current of both the transistor is same, for that we need to short the base and emitter of both the transistors. Emitter is grounded, and this Q1 transistor will be diode connected. Diode connected transistor means the collector and base terminal of the transistor is shorted. So this shorting is very important. This Q1 must be diode connected. If it is not diode connected, then output will not track the input current, right? So this is the basic current mirror that you have already studied. Now, to design base current compensation current mirror, what we do, we add an additional transistor Q3. Q1 and Q2 are already here. Q3 between the collector and base of Q1 transistor. Now we will see that what is the advantage of adding this additional transistor Q3 between collector and base of Q1 transistor. That we will understand with the help of this circuit, that is the current mirror with base current compensation. Now we can see that the input current is I reference, and this Q3 transistor, it is added between collector and base of Q1 transistor. Now, to understand that what is the role of this Q3 transistor and what is the advantage of this current mirror over basic current mirror, for that we need to find out the relation between output current and input current, that is I0 and I reference. So to derive this relation, we need to apply KCL at node X. Now you can see that I reference is coming from upward direction, and one current is IC, and the base current of Q3, let's say it is IB3. So if we apply KCL at node A, then the equation will be I reference is equal to IC plus IB3. IB3 is the base current of Q3 transistor. Further, we can write IB3 in terms of IE3. This is the current IE3, that is the emitter current of Q3 transistor. Further, this IE3 has been divided into two parts. One is the base current of Q1 transistor, another one is the base current of Q2 transistor, that is IB2. So from here you can write IB3, that is equal to IE3 upon beta plus 1. That is the relation between base current and emitter current, and IC plus this IE3 is equal to IB1 plus IB2 upon beta plus 1, right? Because IE3, emitter current of Q3, has been divided into two parts. One is IB1 and another one is IB2. Since Q1 and Q2 are matched transistors, and we can consider this IB1 is equal to IB2 is equal to IB. So we can write IB1 plus IB2 as 2IB. There is no issue in that, because IB1 equal to IB2 equal to IB. Now further, we can write IB in terms of IC. So IB is equal to IC by beta. So after that, just take common IC common, and after that you can find out the relation between IC upon I reference, and of course this IC is equal to I0, because this is the current mirror. Fine. So simply to do the calculation, just apply KCL at node X and simply use the basic equations which you have already studied in basic electronics, and just find out the relation between I0 and I reference, and after solving you will be getting I0 upon I reference is equal to 1 upon 1 plus 2 by beta square. But here one approximation we are taking. That approximation is, you can see this factor is beta into beta plus 1, so it will be beta square plus beta. That approximation is, we are considering beta square is very greater than beta, and this is the valid approximation because beta is very high, so beta square will be very greater than beta. So after taking this approximation, we will get 1 upon 1 plus 2 by beta square. Now just compare the result of this current mirror with the basic current mirror, and see, for the base current compensation current mirror, we are getting 1 upon 1 plus 2 by beta square, and for the basic current mirror we had got 1 upon 1 plus 2 by beta, and this is basically I0 upon I reference. So what we want? We want I naught is equal to I reference. For that, 2 by beta square term will be 0. But you can see that this 2 by beta square term is lesser than, it is lesser than 2 by beta. So the error between output current and input current is lesser in case of base current compensation current mirror. That is the advantage. So current transfer ratio is less dependent on beta, that's fine, and the output resistance remains approximately equal to that of simple current mirror. So you can calculate the output resistance, that is the different topic, fine. And current transfer ratio is less dependent on beta. We are saying it because this 2 by beta square, it is very lesser than 2 by beta. So if in the result, if it is 2 by beta cube, for example, 2 by beta cube, so it will be good. So in that case, the error will be lesser, right? And of course, if beta is infinite, that is the ideal case. So I naught will be equal to I reference, but practically beta is finite. So the advantage of current mirror with base current compensation is that the error between output current and input current is lesser in comparison with the basic current mirror. Now the next one is Widler current source. So to design the circuit of Widler current source, what we do? We just connect an additional resistor Re at the emitter of Q2 transistor. Now you can see that if you remove this Re, let's say Re is equal to 0, fine. If Re is 0, then it will be shorted and it will become basic current mirror, So to draw the circuit of Widler current source, what you have to do? You have to just add a resistor at the emitter terminal of Q2 transistor. It will become Widler current source. Now again we need to find out the relation between I naught and I reference, but before that we need to understand that why we are adding this resistor Re and what is the advantage of this Widler current source over basic current mirror. See, with the help of Widler current source, we can generate low value of currents, for example 5 microampere, 10 microampere, with the help of a smaller value of resistors, Normally in basic current mirror, what happens? If we want lower value of current, for that we require higher value of resistance in basic current mirror. But in Widler current source, to get lower value of currents, we can get lower value of currents with the help of lower value of resistance. And obviously when we design circuits, it is desirable that the value of the resistance should be less. Why? Because it will reduce the area of the circuit also. Because if the value of the resistance is more, the area of the circuit will be more. So the advantage of Widler current source is Widler current source allows the generation of a small constant current using relatively small resistors, which saves chip area. And this small value of current is very much required, like in 741 IC. We use Widler current source at the input side. And also output resistance of Widler current source is high due to emitter degeneration resistance. Like you have studied this emitter degeneration resistance in biasing. This Re provides negative feedback. Now coming to the derivation part. So from the circuit of Widler current source, this is the standard equation of VB1 and VB2. You can calculate this VB1 and VB2 with the help of collector current equation, that IC is equal to IS e to the power VB by VT. This is the basic equation of collector current. So from this equation you can find out the value of base to emitter voltage. Of course there is an exponential term, so we will get this ln term. So VB1 and VB2, we have written it with the help of the collector current equation, which we have already derived in the basic electronics, right? So here we can calculate the value of VB1 minus VB2. Simply we can calculate it just by subtracting both the equations. Now you can apply the KVL in this loop. In this loop, if we apply the KVL, then it will be VB1 minus VB2 minus let's say if we ignore the base current of Q2, then the current flowing through RE will be I naught. So the voltage across RE will be I naught into RE is equal to 0. So what you have to do, just calculate VB1 minus VB2 from these two equations and put VB1 minus VB2 in this equation and just find out the relation between output current and input current. You can see just after rearranging the terms, this is the final equation. I naught is the output current, I reference is the reference current, that is at the input side. VT is the thermal voltage, RE is the emitter degeneration resistance which is connected at the emitter of the Q2 transistor. So this is the relation between input and output current for Widler current source, and this relation is also very important when you do the small signal analysis and DC analysis of 741 IC. There you will require this equation because there Widler current source is used, right? So that will be the requirement. But remember that the main advantage of Widler current source is wherever we require lower value of current, Widler current source is preferred, because with the help of Widler current source, we can generate lower value of current using smaller value of resistor, And if we are using a smaller value of resistor, then the area of the IC, area of the circuit will be reduced. So this is about the Widler current source. Now, coming to the multi-stage amplifier. So I will be covering only the basics of this multi-stage amplifier, by which you will get the insight of multi-stage amplifier, right? So what is multi-stage amplifier? As the name suggests, it is having more than one stage. If any amplifier is having more than one stage, it will be considered as multi-stage. For example, 2-stage amplifier, it is a multi-stage. 3-stage amplifier, it is a multi-stage. 4-stage amplifier, it is a multi-stage. More than one stage means multi-stage. Like earlier in unit 1 of analog circuits, you had studied common emitter amplifier, a common source amplifier. There, like in common emitter amplifier, the input signal is applied at the base terminal, output is taken from the collector terminal. So those amplifiers which you had studied in first unit, those are single stage amplifier. Why? Because you are just giving the input and taking the output. It's a single stage. Multi-stage means the output of the first stage, it will be connected to the input of second stage, the output of the second stage will be connected to the input of third stage, the output of third stage will be connected to the input of fourth stage. It means that in multi-stage amplifier, there is a cascading of stages. So let's draw the block diagram of multi-stage amplifier. So let's say this is the first stage amplifier and we apply the input signal at the first stage. This first stage is also called input stage because the input signal is applied here, right? And the output of the first stage is connected to the input of the second stage. Similarly, the output of the second stage is connected to the input of the third stage. Similarly, the output of the third stage, it can be connected to the input of fourth stage. Let's consider 3-stage amplifier. Fine. So if it is 3-stage amplifier, so V0 will be here. And this third stage, we can say this is the output stage because from the third stage we are taking the output. Fine. So when we cascade different stages, then it becomes multi-stage. But here one important thing. Why we need to connect multiple stages in the cascaded form? Why we need multi-stage amplifier? When we had already a single stage amplifier like common emitter amplifier, common source amplifier, then why we need multi-stage? The reason is that we get very limited gain with the help of a single stage amplifier. But in many applications, the gain requirement is high. For example, analog to digital converters, digital to analog converters. In such applications, there are various other applications also, but in such applications, we require higher gain. For example, in some applications, gain requirement may be more than 80 dB. In some applications, gain requirement may be more than 100 dB, 110 dB. So we cannot get the gain of more than 100 dB with the help of single stage. For that, we need to design multi-stage. We need to go for 2-stage or 3-stage amplifier. So, the advantage of multi-stage amplifier is it provides higher gain, and the gain will be, let's say the gain of the first stage is AV1, gain of the second stage is AV2, gain of the third stage is AV3. So what will be the overall gain of this multi-stage amplifiers? This is a 3-stage amplifier. So the overall gain of this amplifier is V0 upon Vin. Since all the stages are connected in cascade, so the gain will be AV1 into AV2 into AV3. So you can see that if you are using single stage, then you will get only AV1 gain. But when you go for 3-stage, 2-stage, 4-stage, whatever, then the gain is multiplied. So we get more and more gain with the help of multi-stage amplifier. So the need of multi-stage amplifier, it arises in various applications, like I have mentioned ADC and DACs and various other applications, right? And advantage of multi-stage is obviously it provides more gain. But there is one challenge while designing the multi-stage amplifier when we go for multi-stage like 2-stage and 3-stage. When we go for 2-stage, 3-stage, 4-stage amplifiers, in that case, there are various poles and zeros are created, and those poles and zeros are very comparable, they are very close. Due to that, the stability of multi-stage amplifier is compromised. Basically, when we go for multi-stage amplifier, so it is important to check the stability of that multi-stage amplifier. To check the stability, we can calculate the value of gain margin and phase margin. And for any circuit to be stable, the gain margin and phase margin should be positive. Normally for any circuit, the minimum phase margin required is 45 degree, but the optimum value of the phase margin required, that is 60 degree, right? Because in multi-stage amplifier, because of the comparable poles and zeros, the amplifier becomes unstable. So to stabilize that amplifier, we use a technique. That technique is called frequency compensation. Frequency compensation is a technique to stabilize the amplifier. And one of the most popular frequency compensation technique is Miller compensation. Miller compensation. So when we go for multi-stage amplifier, so we need to apply this Miller compensation in the amplifier circuit in order to stabilize the amplifier. That is very important. So in Miller compensation, what we do, we connect a capacitor across the amplifier. For example, let's say there is a 2-stage amplifier. This one is the first stage and this one is the second stage. So what we do in Miller compensation, we connect a capacitor, compensation capacitor CC across this second stage, that is the between the output and input of second stage. So the role of this compensation capacitor CC is to move the dominant pole towards the origin and to ensure that the non-dominant pole moves away from the origin. When this happens, then the phase margin of the circuit is improved, and due to improvement in the phase margin, the circuit becomes more and more stable. So the challenge involved in the design of multi-stage amplifier is that when we go for multi-stage amplifier, we use frequency compensation techniques to stabilize the amplifier. And one more thing, when we go for any multi-stage amplifier, the first stage of multi-stage amplifier is differential amplifier. It is very important to use differential amplifier at the input stage, at the first stage, because differential amplifier has the capability to reject the noise. Because it's a circuit, there will be noise, so we need to reject that noise. For that, the input stage of any multi-stage amplifier should be differential amplifier. That's why when we design any op-amp, that op-amp is basically the multi-stage amplifier, and you will see that the input stage of any op-amp, it's a differential amplifier. In order to reject the noise, if noise is getting rejected, the CMRR, that is common mode rejection ratio, will get improved. And first stage is differential amplifier. The second stage, it may be differential amplifier, or you can use common source amplifier also, there is no issue, fine. And one important thing, that is when we use frequency compensation technique, and that frequency compensation technique is the Miller compensation. So it is important that the Miller loop gain should be negative. It means that if we have connected this compensation capacitor across the second stage, so the loop gain, Miller loop gain should be negative. It means that this second stage amplifier should give the negative gain in order to stabilize the circuit. So which amplifier gives the negative gain? That amplifier is common source amplifier when we go for MOSFET amplifiers, right? It is very important. The Miller loop gain should be negative in order to stabilize the circuit. If it is positive, then the circuit stability is compromised. Then it may form the positive feedback, and the amplifier becomes unstable. So it's an important thing, right? So in this class, I have discussed about different types of current mirror. After that, I have discussed the basics of multi-stage amplifier, need of multi-stage amplifier, and the challenges involved to design the multi-stage amplifier. This is the reference. Thank you.